Yep.
All right, there is no turning back now. We just get started. So today I will tell you about the basics of human-computer interaction. Then, after we discuss various examples and I will provide references to books and research experiments, I will show you how this affects computer security as well. Because people who use computers need some kind of an interface to interact with the system. And depending on how the interface is designed, people can make good decisions or bad decisions. They can choose a strong password or a weak password. They can irreversibly delete some data, or they can do things such that no disasters will happen. But before we switch to that, we have to cover the fundamentals such that you will learn the principles and then learn a little bit later how to apply them to combine knowledge and obtain new knowledge that is relevant in your context. So I will begin my story by telling you about several basic concepts which I think everybody needs to know, regardless of which field they work on. If you have to do an interface that interacts with people, or to be more precise, that people interact with, you need to know these. So the first concept is an affordance. Has anyone ever heard about it?
Mm-hmm.
In which context?
In the design class that we did, we talked about affordances.
Okay, so is everybody exposed to this?
Mm-hmm.
Yeah, you too.
Yeah, I already took that
We
class.
all took the same
Yeah.
class, we all answered.
Yeah.
Okay,
Yeah, you have to
so,
take that class the first year.
An affordance defines what an object can be used for, or what somebody can do with that object. And by looking at the shape of the object, its size, you can apply it in one way or another. Can you give me examples of how we can use affordances to simplify interfaces? Or do you want just me to give you examples and that's all?
We can think about something.
Well, the most common example,
Is the door handle?
yeah. So the door handle. Sometimes you bump into a door that has a push or pull sticker on it. But of course there is a way to completely eliminate that sticker if you choose the shape of the door and the handle such that things are obvious. So if I want to pull something, then I need to grab it somehow.
Right.
So there needs to be some kind of a thing which I can grab and then pull towards me. And if I have to push something, I don't need one such thing. So it is a very common interface approach here in this university. All the doors, they have just a metal plate which you push, and this eliminates the question, do I pull or push? Because there is only one thing you can do. And when you are on the other side of the door, you have a handle, so you know, obviously the only thing you can do is pull. So you know about affordances.
I think Adrian is calling me down, I think.
All right. Don't lose this. Put it on your neck.
Yeah.
Because,
This is the only
yeah, it's the only one, and I don't want us to get stuck. Because we won't be able to go downstairs.
But there's a lady sitting there, right?
Well, somebody is there, but I don't know that person. There's no connection with that. Well. What about the system model and the user model? Does this ring any bells? Maybe in your course this was covered? So imagine that you have...
Yeah, so remember studying with system model is more centric when you think about the system, and when you're thinking about you just keeping the user in mind, and when you build the system, that's a user model, and when you build the thinking system in mind, is that the system model?
Well, you could say that. I mean, what you said isn't wrong, but it's not so clear that it's
yeah.
obviously that what I meant. So let me provide details. You have a system. The system does something. For example, if you press this button, a window closes. If you press that button, something goes up or something goes down. And any system can be described with some kind of a diagram or a flow chart or some algorithm which explains what exactly will happen when this or that occurs. So that's a system model. It is what really happens and how the system really works. A user model, in contrast, is what a person thinks about what happens when they do this or that. So in other words, let us draw. So you have some starting point here. Then there is some decision-making branch, and then the system goes either on this path or on that path. So this is what really happens. But this is complicated. This is what programmers and engineers look at. You don't expect somebody's grandmother to study a flowchart in order to understand how a fridge works or how to turn on the lights. That's not the way things ought to be in this world. So what we have on the other side of the barricades, we have an interface, some buttons, maybe a screen that displays some kind of information, and the person who uses the system, after several interactions, has a model that, from their perspective, describes what happens when you use this system. So, in an ideal world, the difference between the system model and the user model must be a very, very, very small number. Or ideally, there should be no difference. If there is no difference, it means that people fully understand how this works. But this is an ideal case, because today we have very complex systems, and there is no way on earth a human being can fully understand every aspect of what happens. And as an example, think about a car. A car is the result of a super high-tech engineering mission. It's about physics, it's about mechanics, it's about chemistry, how oil burns, how friction occurs in wheels, how you steer. So there is a lot of stuff that goes on in a car. But from a person's perspective, the interface is just several pedals, a steering wheel, and maybe a little stick for changing gears. So what they did is they hid this huge complex system behind a very simplified interface that has just two pedals, a steering wheel, and maybe a few other buttons around them. There can be problems. So obviously, a complex system cannot be understood by a human, so you will have to use analogies, metaphors, or simplify it in such a way that people will be able to use it without having to have a PhD in physics to drive a car. So up to this point, I have to summarize that a user model is what a person thinks happens. A system model is what really happens. The greater the distance between them, the more problems will arise when people use your system, because you expect that clicking this button, the window will go away, but it turns out that when you click it, the window maximizes itself, or you get some completely unexpected behavior. So, the smaller the difference between these two models, the better things are. And today, in a computer age, things are especially problematic. And here's why. In the past, devices were mechanical. You had a little gadget, and you could disassemble it, you could see what's inside, or even most of the system was visible. For example, you know how an abacus looks like?
Yeah.
You know, the thing for counting? So you have some wires, and on each wire you have some disks, and you just move them around, and that's how you do math. So in the case of an abacus, everything there is in front of you, and you see the state of each component right here, right now. You don't need to disassemble, you don't need to pull apart, you don't need to imagine. In the case of a car, things are pretty complicated because it's hidden under the hood. You don't see at which state the pistons are and what the engine is doing right now. You don't see how the fuel burns. You don't see how the spark plugs generate a spark. As somebody who learned about that, you know what's supposed to be happening, but you don't see this happen. So older systems were very simple because what you see in front of you is everything there is to see. As things become more complicated, and computers are a very good example, we have a completely different situation. Because in the case of a computer, you have just a screen. Let's say it has 124 by 768 pixels. But the state of the system cannot be fully expressed just in this output device. The state of a system is just a bunch of bits. You can't see bits. You can't see electricity flowing through your circuits in the motherboard or in the processor. Therefore, there is no way a human can see what a computer is doing like they could do in the case of an artifact like this one. So with computers, we ran into an edge case. There's no way for you to see what's happening unless you have some kind of a visualization thingy in front of you that clearly tells you which state the system is in right now, what's it going to do in the next few seconds, what is the result of the previous operation, and so on. So anybody who makes an interface for software has a heavy burden on their shoulders. It is their challenge to take this super complicated system and visualize it in a very, very restricted two-dimensional plane. Yeah, you have additional bells and whistles like speakers, so you can make a beep every now and then. And you have things like printers. They could show some output on paper. But still, it's not going to get you anywhere as close as where we started from. Or think about even simpler interfaces like some scissors or a rock that a prehistorical hunter used to hunt down a mammoth. The rock is in my hand. There is no state, there is no diagram or state machine that describes what the rock is going to do. The interface is the rock itself. The instrument is the interface. But now we must wrap a complicated system inside some friendly interface. If you have any questions or remarks or you need samples, just let me know anytime and I will provide more. Another important concept is that of information overload. You have a lot of stuff going on right now. While we spent a few minutes here, I may have received some emails, somebody posted something on Facebook, somebody posted something on Twitter. If I were at my computer right now, then throughout this time, I would probably be exposed to 5 pop-up windows, some balloon notifications in the lower right corner. My computer would probably beep or make some sounds to tell me that something just happened. But people don't have an infinite attention span. You can't pay attention to 1,000 things at a time. In fact, there is such a thing as a locus of attention. This is, let's say on the screen, it's one specific area which I'm focused on right now. And this place is only one thing. You can't be focused on multiple places at the same time. There's just one. So obviously, all these pop-ups and balloons and other things that keep popping up, blinking and beeping, they are distractions. In fact, you could see this whole picture as a zero-sum game. Now, the critical resource is a user's attention. And attention works in such a way that if somebody has it, then somebody else doesn't. So the more pop-ups and widgets you have on your screen, the less attention you can dedicate to one that actually matters. For example, imagine that you're running a nuclear power station and something goes wrong and the temperature of the reactor exceeded some threshold. And you have a computer screen in front of you. It would be a very bad design if you had a little tooltip here that says, hey, your reactor is critically hot. And that this pop-up would be of the same size and color as the pop-up right next to it that says somebody just posted a picture of a cat on the internet. So these two pieces of information are competing for your attention. As an interface designer, you should think about ways of reducing the amount of stuff you show to a person at a given moment in time, such that they could pay attention to things that matter. So before you decide to show something on the screen, don't think about the question, which font size and color I should use for displaying this message. Think about, do I really need to display this message at all? Maybe it doesn't really matter. And another thing that I think is important to mention here is an F pattern. It is the result of a study that involved eye tracking. Do you know about Jakob Nielsen? He's a usability expert, and on his website, if you go and look for F pattern, you will see this study and some screenshots. So what they did is the following. They took some web pages with content in them. So you have ads and stuff here, everywhere. And then they set up an eye tracking mechanism which would observe where a person is looking at every moment in time. They would measure how much time everybody spends looking at different parts of a web page. And here is what they revealed. That people look at things like this. So they spend a lot of time looking at the top of the page. Then they spend a lot of time scanning it vertically. And then it looks like this. So the next paragraph or the next line gets less attention, and the lower you go, the smaller it gets. So basically, the lesson here is that if you want something to be memorable, put it here or here. In other words, once you know how people behave, you can choose your visualization such that people are exposed to the most important parts of the information as swiftly as possible with minimal effort.
What was the name of the guy that you
Jakob
Nielsen.
Nielsen.
Jakob Nielsen. I think we talked about that.
Yeah.
About it, right?
Yeah, so that's him. Also, the person that exposed me to these concepts, I'm not sure if he's the one who coined the terms, but he's the one who formalized them. It's Donald Norman. He has a site where he publishes essays about interfaces and memory and attention. I think it's jnd.org. I'm not 100% positive about that, but just look for his name. And
Yeah, Norman. That's another paper that
Yeah,
we had in
so
Matthew's
This
class.
is the same class that we were talking about, so
Mhm.
we read both of these guys' papers.
Yeah, Norman.
He has multiple books,
Yeah.
which are really cool, and the one you should start with is The Design of Everything.
the
Yeah,
everything.
the same book. Yeah.
Yeah.
And then there are other ones you should read, Things That Make Us Smart. I liked it very much. And Emotional Design, it also offers a few interesting ideas which you should keep in mind. And he also has older stuff. One of them is called Memory and Attention, and another one is called Learning and Memory. It's about how people memorize, how they forget. If you tell somebody a story, you can predict what will be the parts they will forget first, and you can also predict what will be the parts they will remember even 10 years from now. And you can also, based on his research and the stuff he describes in those books, you can choose multiple approaches. You can choose one approach of conveying the same information such that you maximize the amount of info people will memorize. So it's very, very interesting. He provides references to studies and raw data. So if you're interested in that, he is definitely the guy you should keep an eye on. Another important concept is that of a mode, which can be explained in the following way. Every now and then, all of us have been exposed to systems that can be in multiple states. And depending on which state the system is in, if I press one button or another, it does one thing, but if the state is different, then pressing the same button gives you a completely different result, or a slightly different result. But the key idea is that it's not the same result. And this has some negative side effects, because the person has to know what state the system is in before they press something. And unless something in your interface adequately reflects the state, people will be confused and they will make mistakes, which can be disastrous in some cases and not so painful in other ones. Has anyone been exposed to this concept?
In case of we were talking about this in class. For example, the iPhone has one button.
Mm-hmm.
So you don't know. I mean, for a person who's not used to that kind of interface, he uses that one button for everything, right? I mean, from moving from one page to another page, you know. I mean, to get to the home screen, it also serves as bringing up the applications, you know, that are currently running. You know, so it has one button has multiple functions.
Okay, so it's the same button, but depending on how you press it, whether it's a long press or a short press,
Yeah.
it does different things. So let me give you a more simple example, and then we will elaborate on that. On keyboards, you have a caps lock key and a numlock key. So this is an example of a state. If caps lock is pressed, then if I press A, I get a capital A. If caps lock is not pressed, then when I press A, I get a small a. In other words, without knowing the state of the caps lock button, I cannot tell you what happens when I press A. So that's a mode. Another example of a mode, has anyone used Vim? It's a text editor mostly used on Linux, for example. Anyway, it's a text editor which is quite complicated because...
BI?
No, VI.
BI. Yeah.
VI editor.
Yeah. Yeah.
Yeah, editor.
Yeah. Yeah.
Okay, so there's VI and there's VIM.
Yeah.
Improved VI.
Yeah. Yeah. The improved.
So you know about it. There is insert mode, there is search mode,
Yeah.
and maybe you also remember how it worked out in the very beginning when you just started using it. Was it easy for you to type some stuff?
No.
In other editors, you just type and you have your text, but in this one, you also had to keep track of modes. Is it in insert mode? Is it in
Yeah.
command mode? So that's-
erase a word or
Yeah,
delete
right.
a letter.
Yeah. So there is such a thing as a learning curve. It's how much you know about the system as a function of how long you've been using it. In the case of, so let's say this is time, and this is the amount of features you have mastered. In the case of, let's say, Notepad, the standard Windows text editor, in a very short amount of time, you already know 100% of the features. It's very, very simple. Let's take a calculator. It takes a bit longer, but you also know how everything works because it's quite straightforward. But in the case of VI or Emacs or GCC or the compiler or some command line debuggers that you use to debug your stuff, the learning curve can be quite painful. You can spend a lot of time and you will never reach the 100% mark. So what separates a good program from a not so good one is the fact that in the case of a nice program, the learning curve is something like this. In a very small amount of time, you reach the top. In the case of programs that are not easy to use, programs that don't reflect their state adequately, the learning curve can be very, very shallow. It will take you a long, long time to be able to create a file in VI and then save it. I mean, if you compare it with Notepad, the delta is obvious. So that's a learning curve, and if you have modes, that's usually correlated with a shallow learning curve. And there are some people who strongly advocate completely modeless interfaces. You have a remark? You did this.
Which?
I thought you raised your hand, but
No.
So a modeless interface is an interface in which when you press one thing, it always does the same result, regardless of how the planets are aligned. In this case, the benefit is that whatever you look at, you don't have to think about other parts which are not visible on the screen, such as which state is the program in right now. If I do this, it definitely does that. And a nice example are Android phones. They have several buttons. A home button, a back button,
Menu,
and
menu search,
The apps.
menu.
search.
And now it's changed a bit. So
Okay, I have to check out what's on mine.
Different or
Search.
different phones?
Back, menu, and search. So mine has these buttons. And what I like about this design is the fact that whenever I press home, regardless of where I am, in which program, or if I'm configuring some settings in some dialer, if I press this, I always get to the home screen. If I press back, the rule is it brings me one step back. So if you represent the state of the,
Diagram and tree.
if you take a tree to represent
Tree representation. Yeah.
what's inside the phone, if I am here, if I press back, it always brings me one step higher, until I reach the home screen. Menu, whenever you press menu, you get that little pop-up from the lower half of the screen. So that it's always a menu. And a search is always a search. If you have a properly designed program that completely follows the conventions of the platform, then what I just said will be true. Of course, a program is free to override this behavior. For example, when I press back, it could do something completely different because, with software, you can program pretty much anything. But if you break these conventions, then this will have a negative side effect on people who use the software. These buttons on an Android interface are a pretty not bad example of a modeless interface. While we're at it, there is another thing you should know about. It's a so-called Quasi Mode. A Quasi Mode is a reasonable compromise. It's something that lets you shift temporarily the state of the system for as long as your action persists. And a typical example is the shift button. So when you press shift and you hold it and you press A, then you get a capital A. As soon as you take your hand off the shift button, the pressing A yields a small a. And the difference is that in this case it requires my active intervention. I can't just press and hold shift without realizing that I'm pressing and holding shift. Whereas in the case of caps lock or insert or num lock, you can press it and you can forget about it. And then when you type in a password, it won't work because caps lock is turned on. Or it happens to me, especially on a laptop. The one I have has a reduced keyboard, so there is no numpad. Sometimes when you install an operating system by default, it boots with numlock on. And when I say, okay, create my user with this password, I type a password, which maybe it uses some characters on the right side of the screen, but instead of letters, it gives me numbers. But of course, I don't see that because the password is behind asterisks. So this is an example in which the system fails to convey its state in a clear fashion. Yes, I could look at this little light. If it's green, then caps lock is turned on, but people don't pay attention to it because today, with information overload, just try this little experiment. Count the number of LEDs you have in your room at any moment in time. Some of them are blinking, some of them are not. They can have different colors. Red means bad, yellow means not so bad, green means all right. When you have so many blinking lights around you, remember that you can only be concentrated on one thing at a time. So the more stuff you throw at people, the less likely they are to pay attention. So a quasi mode is a good compromise because it gives you the advantage of giving more functions to the same control, like a button or a widget, but it lacks the negative side effect that you can forget about which mode the system is in. Now, as I mentioned this part about Android, then it is reasonable to introduce the next keyword, and that's a HIG. Do you know about this? A HIG is a set of guidelines, and this one stands for Human Interface Guidelines. Any operating system or environment or platform that has some self-respect also has a HIG. For example, you can look for the one published by Apple. You can look for the one published for Windows 7. There is one for GNOME on Linux. There is one for Android. So these documents are free. You can download, for example, this one. They're available as online web pages, or you can just download a PDF. What they do is they define a set of conventions that
Human interface what?
Guidelines.
Guidelines.
So what the HIG does is it defines a set of conventions that will help you as a developer create a program that fits in nicely with the rest of the ecosystem. They tell you about things such as the spacing between buttons, the spacing between the button and the edge of the window, or the order of the buttons. For example, if you have some kind of a message box with an OK and cancel button, which one should be on the left and which one should be on the right? Should they be reversed? They also tell you about choosing font sizes or how to define the layout of the controls on the window. Should you spread them? For example, if you have a window like this, you can have an edit box, drop-down list, and an OK button here. And you could have some checkboxes. So should they be aligned like this? Or maybe you should also have another imaginary vertical line which you use to align other controls. What's the space between these two? What should be the default value here and there? So all of these things are defined in the HIG, and it should be one's moral duty to read this document before you create anything for this, or that platform. This will help you make a program that is consistent with the rest of the environment and even consistent within itself. Because if you have something complicated like Microsoft Word, for example, you have tons of dialogues, windows, pop-ups, and it would be great if in all of them the OK button would always be here and the cancel button would always be to its left, for example, such that people could develop habits that they can leverage when they use the program. And the one from Apple and Windows for Windows 7, they have a lot of pictures, a lot of examples of how to do things and how not to do things. Really, even if you just look at the